Hello and welcome to my study of Lab 3, Black Holes and Orbits. Now the purpose of this lab is to study gravitation and orbits, and that includes determining unknown information from observed orbits and designing a desired orbit from known initial conditions. Now this lab relies on the Newtonian model of physics, which is made up of 3 laws of motion as stated below, and this lab specifically relies heavily on Newton's second law of motion. Now, a quick introduction. In the first half of the lab, we were determined to find the mass of a black hole based off an observed orbit. And the calculated mass I found for the black hole was around 1.881 times 10 to the 34th kilograms. In the second half of the lab, we were determined to find the initial velocity that would allow a rocket ship to orbit around a planet and a moon at the same time. As you can see, I was able to create an orbit that has an elliptical path around the planet and every once in a while shoots off around the moon. So for this lab, we needed to use Newton's second law of motion to derive the velocity update and the position update formulas that we were going to use in the GlowScript computational models. Now, the system for the first half of the lab was the black hole and the star, and the system for the second half of the lab was the planet, the moon, and the rocket ship. So, for the first half, the initial conditions were a black hole of unknown mass is located at the origin, and a start mass of 2 times 10 to the 30th kilograms is orbiting the hole. My email generates specific coordinates and speeds that determine the star's initial conditions. By tracking the motion of the star, we can work backwards using Newton's second law to determine the mass of the black hole. And again, the mass was determined to be 1.881 times 10 to the 34th kilograms. On the right hand side, you can see the iterative loop that was used to keep updating the position of this star based off the mass of the black hole. You can see how we start by finding the initial and final velocities, the initial and final momentums, and then we use those values together to find a change in velocity, a change in momentum, and this change in momentum allows us to find the net force, which allows us to calculate the orbit for the star. Now, moving on to the second half, where we're determining orbits, the initial conditions are a moon is orbiting a planet, and your rocket ship starts on the moon, and we want to create an orbit around the planet and the moon. We must take into account the force of gravity from the planet and the moon to determine an initial velocity that will send the rocket into an orbit around the moon and the planet. The initial velocity I used was 50 meters per second in the negative x direction and negative 130 meters in the negative y direction. Again, on the right hand side, you can see the iterative loop that I use to continuously update the velocity, momentum, and net force acting on the rocket by both the planet and the moon, which is what allowed me to continuously calculate the orbit. Now, what does it mean? Well, the force parallel causes a change in only the speed or the magnitude of the velocity of a vector, while force perpendicular causes a change in only the direction of motion, whereas a change in momentum over time is an observable change in the speed, and similarly, for the perpendicular change in momentum over time, it's an observable change in the direction of motion. So what's important about this is that a force causes these changes in motions, but a force can't be directly observed. Only its effects can be observed. But momentum and its change can be directly observed. Now what if? If our calculations also included the black hole and the star, we would need to calculate the interaction between all of the previous objects in the system and the 2 new objects. The dominating force would come from the black hole because it is so massive. If the star was in a steady orbit around the black hole and the planet was in a steady orbit around the sun, it would likely not change the initial velocity very much. These massive objects can cause changes in the orbital paths, however. For example, the sun's mass causes the orbit of the moon to rotate about every 9 years, and there would likely be similar effects by adding in the 2 new massive objects. Now, what can we come away? This lab shows that Newton's second law of motion can be used in 2 different directions, Given observed motion, the mass of an object can be calculated by working backwards. It can also be used to create a predicted path of motion from knowing starting conditions. This makes Newton's second law of motion an extremely useful tool for physicists. Thank you.